Hello everyone, welcome back to Chem-O-Notes. Did you know that we can predict UV visible absorption of compound just by simple rules without any instrument? So let's begin. UV spectroscopy part 1. And in this video you will be learning how to calculate lambda max using Woodward-Fieser rule. So stay tuned with Chem-O-Notes and please subscribe, like and hit the bell icon for more notification. So grab your notebook and let's begin. So let us understand the primary use of UV visible spectroscopy is to study conjugations and electronic transitions in the molecule. It helps us to identify the presence of conjugate system. Like you can see here in this sample or this molecule which is shown on the screen, there is a conjugation. Double bonds are in conjugated. So such conjugation systems, conjugated systems, double bonds and even the aromatic or transition metal complexes we can detect using UV visible spectroscopy. So in this video, we'll explore the main use of UV spectroscopy and learn how to find out or calculate the lambda max for conjugated dienes using Woodward-Fieser rule. This concept is super important for your competitive exams, any exams like NET, SET, GATE. So stay tuned and grab your notebook. Let's start. So students, let us first understand what is Woodward-Fieser rule to calculate the lambda max. So this Woodward-Fieser rule deals with basically the dienes and unsaturated conjugated carbonyl compounds, which are also known as enones. Okay, enone system. So in this video we'll be basically first understand the dienes, and the next video I'll prepare for enones. The general approach for calculating the lambda max value is by calculating the absorption lambda wavelength for a parent chromophore. Now this table will tell you which type of chromophores or the dienes are there. Okay, for example, the structures may be different types of dienes. You can uh, try to find the lambda max R. Like we can have a linear conjugations, which are also known as acyclic conjugated dienes. As you can see here, I've shown one example: C double bond, C single bond, then carbon double bond, then single bond. That is alternate, you will find double bond and single bonds. Okay, if they are in a linear form, then such dienes are known as acyclic conjugated dienes. Similarly, the next one you can see cyclic homoannular diene. So homoannular diene means a ring which is having, homo means same. So in a same ring, if you have a diene, then it is known as homoannular diene, and it is cyclic because it is a ring structure. Then next is semi-cyclic diene. So one double bond in a ring and other is exocyclic. What do you mean by exo? The ring will have a double bond outside the ring. It is called as exocyclic. So if the diene, you can see here, double bond, then single bond and again double bond. But one double bond is in the ring and other double bond is outside the ring, and they are in conjugation. They are in conjugation. So such type of ring we will call it as semi-cyclic diene. Then next one is homoannular diene, where you will find there are two rings and both the dienes which are, we can say the conjugations are actually exocyclic to the other ring, that is ring number 2. We can write here, let me write it here. One we can call it as ring number 1 or A ring and B ring. We can even denote it them by, let me write down. So for example, if I'm writing this as A ring and this as B ring. So for B ring, these two double bonds are exo. Okay, these two are exo. Whereas for A ring, they are homoannular diene. So this is how we can differentiate the dienes. Then the next one is Heteroannular dyne. Heteroannular dyne, that is two double bonds are conjugated but present in two different rings. So there is a dyne, but dynes you can see here. I will show this with the highlighter. You can see here the dynes are how double bond, single bond and double bond. But both the double bonds are in different rings. Okay. Let us again name them as cycle 1 and cycle 2. So the two cycles or the rings are different and the dynes are in both the rings. Okay. If such is the case of the dynes, then they can be classified as heteroannular dynes. So once again, just go through this table. You can take even the screenshot and write it down in your notebook. Okay. Once you understand the types of dynes, then we can see the tables, how they are, what are the values. So without using the instrument, how we can calculate the lambda max value. Let us understand. Next is, this is the dyne system for whatever different types of dyne we have seen in the previous part. You can find how to give the values for each type of dyne. So basically this table is very important. As you can see here, the table is very important. Without instrument we can write the values and calculate the lambda max value. So basics lambda max for unsubstituted conjugated dyne or acyclic or heteroannular dyne. So any type of dyne, if it is there, then the base value will be, we will write it as 215 nanometers. Nm is the unit for this, okay, for lambda max, because it is wavelength. So we are going to write 215. Then for homoannular double bonds, if there is a homoannular dyne system and there are double bonds, so each one will be given by 39. Both double bonds we will be giving 39 value, we will add to it. So basically you are going to add whatever are the extra things in that ring. These values are given here. Extra double bond in conjugation, if it is there, then we are going to add 30 to this 215. Then exo double bond, if it is there, add 10 nanometers if a double bond is exocyclic to the two rings. So exocyclic to two rings, if it is there, then you will add 10 nanometers. Otherwise single, if it is there, then we are going to add 5 nanometers. Then substituted olefinic carbons, like you are having all these substitutes on the olefinic carbons. Hydrogen, no value we will add, but allylic groups if are there, then we are going to add 5. Halogen, if it is there, we are going to add 5 nanometers. OH group, OR group, again 5. Then ester group, we are going to add 0. SR group, we are going to add 30. NR2 group, we are going to add 60, and so on. So this is a base table. Using this base table, we are going to solve some numericals, how to calculate lambda max using UV spectroscopy. So let's begin. So the first example is a simple linear, you can see a dyne. Okay, what is the example given here? CH2 double bond CH3, then CH3 and CH2, correct? For such type of acyclic conjugated dyne, what we are going to do, we are going to calculate how much is the lambda max value. Calculated and observed, both we are going to see. So the name of this compound is 2,3-dimethyl 1,3-butadiene. You can see here, we can number it as 1, 2, 3 and 4. So second carbon there is a methyl, third carbon there is methyl, so it is 2,3-dimethyl 1,3-butadiene. Okay, so let us start calculating it. We are going to find the lambda max value. So for this, first thing what you are going to do is write the base value. And from the previous table which I have shown you, the base value for dynes is 215 nanometer. Okay, next is, you can see For the olefinic, the carbon, how many are the substitutes? So this is olefinic carbon, that is second carbon and third carbon is olefinic carbon, where you can find there are alkyl groups. So these are your alkyl groups, CH3 and CH3. So how many groups are there? Alkyl groups, 2 groups. Okay, 2 alkyl groups attached to the olefinic carbon. 2 alkyl groups attached to the olefinic carbon. So each one we are going to add 5. So there are 2. So we are going to add 10 nanometers. Okay, add 10 nanometers. And there is nothing else is in this dyne. So your lambda max value will be 225 nanometers. How much it will be? It will be 225 nanometers will be the lambda max value by calculations. So this is a calculated value. Okay, we have just now calculated without any instrument, and if you see by instrument, the lambda max value is same. Okay, it is same, that is 225 observed value. Understood? So this way, without instrument, we can calculate the lambda max value for UV visible spectroscopies using your Woodward-Fieser's law or rule. So let us see the next example. If you see the next example, you will find it is a dyne, but here there are 2 rings. Let us number them as ring number 1 and ring number 2. So if you see the conjugation, see here, there is a conjugation, that means it is a dyne. Double bond, single bond, double bond, correct? So it is a basically a dyne is there. But which type of dyne? You will find for second ring, this double bond is exo. Okay, this double bond is exo to, let me write it here. The double bond is exo to which ring? Ring number 2. Ring number 2. Okay, so this, all these things you have to find out, and then you have to add it in your base values. So let us start how to calculate the lambda max value. First thing is base value. What is the base value for the such type of rings? The base value remains same, that is 215 nanometers. Then there are, how many substitutes are there? Olefinic substitute. So let us see, this is 1, okay, 2, then 3 and 4. So how many? 4 alkyl substitutes are there. Okay, 1, 2, 3, 4. So 4 alkyl groups or substitutes groups. So 4 into 5 is 20 nanometers. Okay, 20 nanometers. Then what else you are going to add? 1 exocyclic double bond. Cyclic double bond. Okay, one sec, I'll just rub this. 1 exocyclic double bond. For double bond, I am writing dB. So it is 0.5. 5 nanometers you are going to add to it. And the total will be 215 plus 20 plus 5. So it comes out to be 240 nanometers. Okay. So this is your lambda max calculated. And if you see, using the instrument, observed, I'll write it down here. It is 238. So hardly slight difference is there. Okay. So you can, without instrument, we can calculate the lambda max value in this fashion. Let us see the next one. Now the next example you can see on the screen is, there is a dyne. You can find there is a dyne here. The dyne system is there, double bond, single bond, double bond. Again there is one double bond which is exo to the ring. Okay, So let us start writing. Base value, first of all we'll write the base value and it remains the same. The base value is 215 nanometer. Then what else? We are going to write the substitutes. How many substitutes are there? Let us see. This is one. Okay, olefinic substitute we have to calculate. This is second, third and fourth. So there are 4 allylic substitutes. Okay, allylic substitutes. Allylic substituents. So N is left out here. Let me write it. STUENTS, substituents. So how many are there? 4. So 4 into 5 is 20 nanometers. Okay, and the next one is, I'll just write it down one below others so that we can have while calculating. This is the base value. Base value for Dienes, as we have seen, it is 215 nanometer. And what is the one more thing, there is exocyclic double bond. So it is 5 nanometers. Okay, so just calculate it. It comes out to be again how much? 240. Correct? If you add them up, it is 240 nanometers. So this is your lambda max calculated. Okay, lambda max calculated. And if you see the observed for this, observed value for this is 232. Okay, so let us go to the next one. Next one, if you can see, there is a homoannular diene and there is a conjugation diene. So let us begin. Base value is 215 nanometers. Correct? Now this is as you can see, there is a conjugation and there is one more. What? In this you will find homoannular diene is there, which is having. So for homoannular we are going to add 39. Okay, 39 we will be adding in this. Just refer your table so that you can write down. Then let us calculate the alkyl substitute for the olefinic carbon. So this is one. Then for this double bond, this is one, and there is one more. You are not going to calculate this, okay? You are not going to consider this because this double bond is not in conjugation. Can you see? After this double bond, there are 2 single bonds. So this is not going to be considered. Okay? So only these 3 alkyl groups. Now these 3 alkyl groups which are there. So 3 alkyl substitutes. That means 3 into 5 is 15 nanometer, and just add them up. That is 215 plus 39 plus 15. It comes out to be 269 nanometer. So your lambda max value calculated is 269, and observed, if you find out by instrument, it was hardly there's any difference, that is 265. Okay, not 2, it is 265. So you can see that using the Woodward-Fieser rule, we are just near the value of observed values, very close. Okay, so using such things, such method of rule, that is Woodward-Fieser's rule, we can calculate the lambda max value in your competitive exams very easily if you know the base values. Okay, so if you know the table, and it is very easy. If you solve 10 numerical such in such way, automatically the values will be by heart to you. So let us go for the next one. For next one, you will find there are two rings, and there is a conjugation here. One double bond, single bond, double bond, single bond, and again double bond. And one of the double bond which is in conjugation, you will find it is exo to the ring. So there are two rings, ring 1 and ring 2. So let us start. Base value we will be writing. Base value, yes student, how much is the base value we are writing? It is 215 nanometer. The next thing what you are going to do is, for conjugation you will find the alkyl groups, correct? Let us find the alkyl groups. The alkyl group is 1, then olefinic alkyl groups 2, here 3, correct? So there are 3 substituents, and one more thing you have to find out, that for homoannular there is extended conjugation, correct? This is your homoannular, and for it there is an extended conjugation, because the conjugations there are 1, 2, 3, 4, 5. So there are 3 double bonds which are in conjugation. So we will call this exo as extended conjugation. So we have to give the value of extended conjugation also for this. There are 3 things we are going to write. One is homoannular, because there is a ring which is having 2 bonds in the same ring, that is ring number 1. Ring number 1 will be called as homoannular. Homoannular, correct, ring. So we are going to add, for such thing we add 39 nanometers. Then there is extended conjugation. Ring number 2 has a double bond which is extended conjugation. So for extended conjugation we add 30, correct? Extended conjugation, there is a spelling mistake, I'll rewrite the spelling. Conjugation, we add how much? 30 nanometers. The next is, there is exo, 1 exo double bond. For that we add how much? Yes student, for, is there 1 or 2? There are 2 actually. If you see how to, here for ring number 2 this is exo, and this is also exo. Okay, this bond is also exo to ring number 2. So there are 2 exo double bonds. So 2 into 5 is 10 nanometers. 10 nanometers we will be adding. And how many substitutes are there? The blue one which I have marked here, there are 3 alkyl substitutes, olefinic alkyl substitutes. Okay, 3 means 3 into 5 is 15 nanometers. So total if you add them up, 215 plus 39 plus 30 plus 10 plus your 15, lambda max value calculated comes out to be 309. 309. Okay, so let us do the 6th one now. 6th one is similar to the 5th one. You can see there is a homoannular ring, then there are exocyclic exo double bond for ring number 2. For ring number 2, this one, that is, I'll show it a highlighter. This double bond is exo to ring number 2, and there is extended conjugation, double bond, single bond, double bond, single bond, double bond. And ring number 2, whatever is the double bond, it is in conjugation. So in the similar fashion, let us calculate lambda max value. Base value is 215 nanometer. Okay, then similarly homoannular ring system is there, so we will add 39 to it. Then extended conjugation, or extended conjugation, how much we add? We add 30, correct? So add 30 to it. Then what is else? There is one exo double bond. One exo double bond. One exo double bond, we are going to add 5 nanometer. Then let us find out the alkyl groups. 1, 2, 3. There are 3 alkyl groups. So just add 3 to it. So if you add 3 to it, how much it will be? 3 alkyl groups in on olefinic carbons. So 3 5s are 15 nanometers. So just add them up. 215 plus 39 plus 15 plus 5. So at last lambda max value calculated comes out to be 304 nanometer. Okay, 304 nanometer. Previous it was 309 nanometer. So this way, using your Woodward-Fieser rule, we can. Okay, let us see the next example where you can find there are two rings where you will find that there is a ring number 1 and ring number 2, and there is a conjugation. You can see here double bond, single bond, double bond, single bond, double bond. So there is a conjugation, extended conjugation is there, plus this double bond which you can see here is exo to both the rings, ring number 1 as well as ring number 2. It is exo to both the rings. So let us calculate the lambda max value now. First we will write base value. So how much is the base value? It is 215 nanometers. Then extended conjugation, there is a extended conjugation. Extended conjugation. So for extended conjugation, how much we add? We add 30 nanometers, correct? After that, what else is there? The exo part, exocyclic double bond. So how many we are going to write for first cycle? You can see here for first cycle this is double bond is exo. Similarly for second cycle double bond is exo, and it is in conjugation. It is in conjugation. So we are going to write 2 exocyclic double bonds. 2 exocyclic double bonds. That means 2 into 5 is 10 nanometer. Then next what else is there? Okay, alkyl groups. We have to find out how many alkyl groups are there on the olefinic carbon. 1, 2, 3. Okay, and for this again there is one more, 4. So all the 4 are olefinic carbons. So there are 4 substitutes, we can say 4 substituents. So 4 substituents, what we write? 5 into 4, that is 20 nanometers. So let us calculate the lambda max value. The lambda max value comes out to be, let me write with black. Lambda max value calculated is how much? 215 plus 30 plus 10 plus 20 comes out to be 275 nanometer. Okay, this is the calculated lambda max value. Let us go to the next one, that is 8 numerical, where you can find there are how many rings are 1, 2 and 3. 3 rings are there, and if you find the conjugation, there is an extended conjugation, double bond, single bond, double bond, single bond, double bond. So there is an extended conjugation. And one more thing you have to observe is for ring number 1, this double bond is exo. Okay, ring number 1, this double bond is exo. Similarly, ring number 2, this double bond is exo. So there are 2 exocyclic double bonds. So let us calculate. Base value is So this numericals are very easy to solve. 215 is the base value. Extended conjugation, students, how many are there? Extended conjugations. There are two extended, that is there is a extended conjugation, so we are going to add 30 nanometer. One extended conjugation we can have for a double bond. Then there are two exocyclic double bonds, so it comes out to be 10. 5 into 2 is 10 nanometer. And one more thing is we have to calculate the substituents. 1, 2, for this double bond there is 3, and for this double bond this is 4. So there are in all total 4 extended conjugation or substitutes. Substituents are 4. Correct? 5 into 4 is 20. Anything else? No. Nothing is there. So we will try to calculate the lambda max value. And lambda max value calculated comes out to be, that is 275 nanometer. Okay, students. So this way we can calculate the lambda max value without using the instrument. Directly, theoretically, we can calculate the lambda max value. Now, I think you have done sufficient amount of practice. We have done just now. There are few examples which you can do it as a homework or practice examples, and just comment below whether you could solve all these 6 numericals which I have given here. If not, I can solve them and upload one more video for you, but just comment below and tell me whether you could solve this. And if you like the channel, please subscribe, hit the bell icon, and like, and do share with your friends who are going to give some competitive exams like CSIR-NET or studying for MSc. Okay, thank you for watching. Do watch the other videos from the playlist @Chem-O-Notes. You can find solved numericals based on the spectroscopy of NMR also. So go and visit the playlist. Thank you for watching. Stay tuned. Bye till then.